Yes.
Okay. Okay. So, any questions about the previous lecture yesterday about pathwise results, local time? It was a bit dense. Sorry. No question about yesterday's lecture? I can't see the chat screen, so if there's a question in the chat, you tell me. Okay, so what we did so far, yesterday in particular, was we focused on.
But sorry, Rama, I think that the slides are a bit small, perhaps.
It's small.
Yes, if you do full screen, perhaps. Okay, that's a much better. Thanks.
So what I did yesterday was to derive as much as possible pathwise results, which hold for any path, any continuous path in the setting I discussed, and without any probabilistic assumptions on the signal, probabilities of transition, nothing. So, and we saw that actually you can derive a lot of results without making probabilistic assumptions. And in particular, what was important is that I tried to show you that you can assess the optimal choice of the threshold delta in these mean reversion trading strategies based on the roughness of the path of the signal, and without knowing its distribution or any assumption on the dynamics of the signal, just the roughness. So that's very important because it goes against all the literature on pair trading, which from page one assumes some stochastic differential equation or some time series model for the signal. So what we did yesterday is, I think, is interesting because it does not assume anything about that. And it shows that the only thing that matters is the roughness of the signal for the choice of this delta. Nevertheless, if you do make assumptions or if you do have information about the distribution of the signal and its probabilistic properties, then you can say much more. And that's what I'm going to do today. And it opens the door to a beautiful chapter of stochastic analysis called excursion theory. So that's what I want to discuss a little bit today. So Ito's excursion theory, and then some applications to our problem, but in the Markov case. Okay, so from now on, I'm going to, in this lecture at least, I'm going to consider the case where the signal we're interested in is a Markov process, more precisely, a strong Markov process. So what is the strong Markov process? Well, it's a process which has a strong Markov property. So you may be familiar with it. Just to recall, it means that for every finite stopping time, if you look at the future evolution of the signal after the stopping time, so s stopping time tau, so the future evolution is st plus tau, where t is positive. And if you call the history of the signal up to time tau f tau, then the strong Markov property says that the future evolution is independent of the past before tau, conditional on the present value. So if I know the present value s of tau at time tau, then I don't need to know anything else about the past. The future evolution only depends on s of tau and not on the past. Okay, so now this is a property that you have for many classes of processes, Brownian motion, Levy processes, but also solutions of stochastic differential equations, diffusion processes satisfy this property. Now, the relation with excursions is the following. So if you look at such a process and you consider now a particular stopping time, the first hitting time of 0, which we denoted T0s, Now, this is stopping time, and if the conditions on the process ensure that this is a finite stopping time, you always reach zero in a finite time, then, well, we can apply the strong Markov property, which then tells us that the evolution of the process after it reaches zero for the first time is independent of its history before reaching zero. Okay. Now, there's nothing special about the first hitting time. You can do this for the second hitting time, the third, and so on. So if you now repeat this, you see that so each excursion will be independent of all the previous excursions. So this is very interesting. It means that the excursions from zero, so excursion from 0 to 0, you look at every time you hit zero, it's a new excursion, then you the next one, and so on. If you look at the collection of excursions of the strong Markov process, excursions from zero, they are independent. And we call E0 the space in which these excursions lie. It's a space of paths which go from zero. So this means that the excursions of from zero of a strong Markov process are going to be a family of independent random variables with values in this space of excursions E0. Now, this is very interesting because we did not assume that S has independent increments. There's no independence property in S. S is a Markov process. In general, it is going to have dependent increments. So if you take fixed times, like a fixed time grid, 1, 2, 3, 4, whatever, and if you look at the increments of S along fixed times, they're not independent in general. They have a very complicated dependent structure. But this result says that, if you slice the path not at arbitrary times, but you slice the path at hitting times of zero, then strong Markov property tells you that these slices, which we call excursions, are going to be independent. Now, this is it seems a trivial thing, but it's actually a very important thing because it means that if you look at the traditional way people model stochastic processes, they build time series models, or they look at the distribution of increments at fixed times. But what this slide is saying is that, maybe that's not the correct way, because you're going to get a bunch of very complicated dependent variables. But if you slice them at these hitting times of zero, then you have independent objects. Now, even more, if you make a slightly stronger assumption that the Markov process S has stationary transition probabilities, meaning that if you look at, so a Markov process is completely characterized, the law is completely characterized by the transition probability. So if I know the probability of ending in a set A after time H, starting from a given state X, this is all I need to know from to characterize the Markov process. If these transition probabilities are stationary, meaning that they only depend on the difference between the starting point and the arrival point in time, then not only the excursions are going to be independent, but they're going to be identically distributed, because it means that every time I hit zero, well, the transition probability starting from zero and going somewhere, it's always the same. It doesn't depend on time. It only depends on the starting point, and the starting point is zero. So it means that these excursions will not only be independent, they will be independent and identically distributed. So what we are saying is that the strong Markov process, if you have a strong Markov process with stationary transition probabilities, I'm not saying that S is stationary, I'm not saying that S is a stationary process, it has stationary transition probabilities. That's different. For example, you can have Ornstein-Uhlenbeck, which is not stationary, it starts from a deterministic initial value, but it will have stationary transition probabilities. So if S is of this type, then if you look at its excursions from zero, you get a bunch of functions going from 0 to 0. And well, this family of functions is going to be a collection of independent and identically distributed variables with values in the space of excursions E0. Now, this is very interesting if you follow what I say. Now, this is very interesting because modeling an IID family is much easier than modeling, stochastic differential equation or some, a process with the generator or kernels or whatever. To model a family of IID variables, you just need the distribution. You just need one distribution. It's a static object. So bye-bye, SDEs and complicated things. You just need one distribution. But of course, it's this distribution is an infinite dimensional distribution. It's a distribution on the space of excursions. Okay, fine. So it seems like we have paid some price. Our price is to go into infinite dimensions. But as I will try to illustrate, and as has been shown by Ito, this infinite dimensional viewpoint turns out to be very fruitful. There are other examples of infinite dimensional viewpoints in stochastic analysis, but in this case, it seems like you go to infinite dimensions, but you move from a time-dependent object with, a differential description into a static object, which is just a distribution on the space of excursions. So it seems that if I give you this distribution, then you know everything about the excursions, and that's true. So Ito famously said when he was doing this work that it became my habit to observe even finite dimensional facts from the infinite dimensional viewpoint. And this is exactly what's going on here, as we will try to see. So this slide is very important. Are there any questions about this? Why the excursions of a strong Markov process lead to IID excursions? So if you understand this, then the rest is trying to identify this distribution, basically. The rest is the excursions of a strong Markov process with stationary transition properties form IID family. So we want to describe this IID family, but IID family is described completely by distribution. So now we want to say, what is this distribution? What does it look like? Can we describe it analytically? Can we calculate it? Can we estimate it? So on. So that's what I'm going to do for the rest of the lectures. But as you can guess, it's an infinite dimensional distribution, so it might be a bit tricky, but it's not inaccessible, and we know a lot about these things. We will see that we can compute, estimate, simulate, do everything. So that's the goal here. But obviously, because it's infinite dimensional, there's some tricky things. And there's another tricky thing. If you pay attention to this slide, I did not say IID sequence. I said the IID family. And unfortunately, as if you followed what we did yesterday, the excursions from 0 to 0 of a regular process, a regular path, cannot be formulated in terms of a discrete sequence because they can be infinitely many in a finite interval, and it's actually a continuum. So so there are two problems here. One is the excursions do not form a sequence. They're not discrete. They may be infinitesimal excursions which lead to IID family, continuum family. And then the second thing is, well, it's an infinite dimensional thing. So what is the distribution in infinite dimension? How do you deal with that? So there are two technical difficulties, which are not light difficulties, but luckily for us, Ito dealt with both of them, and he will show us how to deal with them. Okay, now let's get into the details. What is this family, possibly infinite family of excursions? So how do you describe it, and what does it mean, the distribution of this thing, and so on? So now from now on, I'm going to take S to be a standard real-valued Markov. Standard means it satisfies some regularity assumptions. I'm not going to go into the detail here. So S is the real-valued Markov process. Think of it as your trading signal. It's going to have a mean reversion around 0, but that's not necessary for the theory. And I'm going to denote Px as usual in this theory, the law of S given S0 equals X. So I'm going to assume that this S has stationary transition probabilities, meaning this holds. The theory can be done for time dependent. It's just that you have to put time indices everywhere. And okay, now how do you describe the excursion process of S? So we did that already yesterday for a single path, and it's going to be the same. So we're going to apply what we did yesterday, all the hard work we did yesterday, we're going to apply to the paths of S. So nothing different here. So we assume that S has some occupation density at 0, which we call LT of S. And so what we saw yesterday is that the natural way to, let me go back to the slides yesterday because it's useful. I have the definitions on the slides yesterday. Can you see this? Yeah? No? Okay, so yesterday we defined these notions, occupation, density, and so on. So we said that a path S, and here we're going to consider sample paths of a Markov process, but exactly the same thing. We said that a path S admits an occupation density if the occupation, the measure of the path, which says how much time I spent in each set A, has a Lebesgue density, and we're interested in the occupation density at 0, which we denote LT of S. So an important notation I introduced was what we call inverse local time at 0. So we said that, the more time you wait, the more you hit 0. So the occupation density at 0 is increasing with the time index t. So if it's an increasing function, it has a right continuous inverse, which is defined in this way. You take a level lambda and you call tau lambda the first time when the occupation density at 0 reaches lambda. So if you wait long enough, it will go through 0, and each time it goes to 0, the LT of S is incremented. So when it reaches lambda, that's the first time it reaches lambda, you call it tau lambda. So tau lambda is the inverse of LT. And the crucial remark is this, that an excursion from 0 is by definition a path, a piece of your path S, which it goes away from 0. So when you're on an excursion, you're not at 0, because if you reach 0 again, the excursion ends. So along each excursion, you are not going to increase the occupation density at 0 by the definition. So LT increases on the set where you are at 0. So when you're away from 0 along any excursion, LT is constant. So it means that along excursions away from 0, the occupation density at 0 does not increase. So it has a constant value along each excursion. So we can use the occupation density at 0 to label excursions away from 0, because by definition, along any such excursion, LT has a constant value. So LT is going to be piecewise constant. It's going to increase by steps. And each step is one excursion, exactly. Now its inverse, tau lambda is the inverse of L. If you have a piecewise constant function, the inverse has vertical jumps corresponding to the constant plateaus of L. So tau is going to have jumps, and the discontinuities of tau are exactly the excursions of S. Okay. So this is how we're going to label the excursions. And all this trick is because the excursions are a continuum. So you have to have a way of indexing this continuum family, and the the inverse local time and the occupation density give you a way to index this. So as the occupation density is constant along excursions, so each excursion has a well-defined constant value of LT, and if this value is lambda, let's say, then we call this the excursion with label lambda. Remember that the label is not time, it's an occupation density of S. Okay, so what is the excursion with label lambda? Is simply this. So remember this inverse local time here translates occupation density into time. Okay, so tau lambda is the first time when the occupation density reaches lambda. So to switch between time and occupation density, you use tau lambda. So and tau lambda minus is the value of tau lambda before the jump, is the starting point of the excursion. Tau lambda, so the value after the jump, is the time corresponding to the end of this excursion. So, and the duration of the excursion is exactly the jump of tau lambda. Tau lambda minus tau lambda, right? This is the jump size of tau lambda. The discontinuity of tau lambda is exactly the duration of the excursion, okay? And the excursion is just a piece of S, is the piece of S which starts at the beginning of the excursion and ends at the end of the excursion. So just you cut out a piece of the path of S, and that's this piece is a piece going from 0 to 0. You start at some time where it's at 0, and then you end at the first hitting time of 0. So this is the parameterization. Okay. So we're going to do that exactly here, just apply to the path of this Markov process. Okay, now, so this defines, so what is this doing? This operation is just you take the path of S, it goes to 0 many times. Every time it goes to 0, I cut. The scissors with which I cut is tau lambda. It tells me where to cut. It cuts at the hitting time of 0. And then I get a bunch of excursions. These excursions have different shapes and forms. Some of them go up, some of them go down, some of them are very go high, some of them go very negative, so on. So I have a bunch of excursions. I can think of them as points in the space of excursions. And now the idea of Ito is to say, well, if I want to describe now this set of excursions, how can I describe them? Well, so you take a nice continuous path, you cut it into pieces, which are the excursions. Now these pieces lie in the space of excursions. So I'm going to describe them. It's not a natural idea, but I'm going to describe them by counting where they are in the space of excursions. So what does it mean? It means that every time you give me a set of excursions, gamma, so gamma is a subset of the space of excursions, I'm going to count how many of these excursions fall in the set gamma. So this is the description. Number of excursions in set gamma, you just add indicators of gamma across all the excursions. And as we saw, the excursions are labeled by these occupation density L. So I will, so as L increases, it's like timing, increasing time is like increasing L. So instead of counting the number of excursions in gamma up to time t, the natural thing with this parameterization is to count them up to occupation density L. So this is what Ito defined. And so Ito called this the point process of excursions of the process S. So what is the point process of excursions? Is you give me an occupation density level L, you give me a set of excursions gamma, and I count how many of the excursions that I cut from the path of S up to occupation density L, how many of them fall in gamma. So this is a counting process. So this defines a counting process on the space of excursions E, which counts the number of excursions of a certain type up to the time when the occupation density reaches L. Okay? So this object is called the point process of excursions, or the excursion process associated to S. This is what Ito defined. And this is Ito's description, Ito's way of describing the excursions of a process. So it is a counting process on some space. Okay, it's an infinite dimensional space, but that doesn't matter really. That's not really a problem. And it contains all the information about the excursions of S, because it says what their shape or form is. Gamma can be like the set of excursions which exceed some level. Epsilon, it can be the set of excursions which have a duration longer than one. Anything you want, you can count the number of excursions in there. And it also tells you the timing of these excursions through the label L. But as we saw, the natural, the way in which Ito defines it is not indexed by time t, but by the occupation density of S, which is somehow the intrinsic time associated with S, okay, not chronological time. Okay. Any question about this bizarre object? Okay, so this. Now, okay, so I don't know how much you know about point processes, but this is a very quick summary of what the point process is. So you're all seeing point processes. The example of point process is a Poisson process. So more generally, a point process is on a space E. It's something that counts events in E. So you have so you think of a bunch of events in some space E. So events occur with values in the space E. So they occur in time. So, and then a point process is to each time t and to each subset of E, which I call A here, you associate a number which counts MT of A. So MT of A counts the number of events which happened in the set A during the time 0t. So obviously, if you fix A and you increase t, it's going to be an integer value process. And if you fix t and you look at A, it's a measure, because if you take two sets A and B and take the union, well, the count is the sum of the two counts and so on. So this is called the point process. It's a collection of counting processes indexed by sets of E. So the most well-known examples of point processes, probably you've encountered this in your in the past, are Poisson point are the Poisson point processes. So what is a Poisson point process? It's a point process on E, which has two properties. First is that if I fix the set A, then and I look at the number of events in A up to time t, this is a Poisson process with some intensity, not a standard Poisson process. It's a Poisson process with some intensity, which obviously will depend on A. So for a Poisson process, the intensity can be defined as the expectation divided by t. So if you have a Poisson process t, a Poisson process with intensity lambda, the expectation at time t is lambda t. So you can always define the intensity as the expectation of the Poisson process divided by t. So okay, so this is it will have some intensity which depends on A. And eventually we allow this to be infinite. We don't necessarily try to refine it. We allow this to be finite or infinite. So if a process is infinite, we also call it the Poisson process. If it has infinite mean, it's okay. And then the second property is independence. It says that if you take two sets A1, A2 that are disjoint, then the Poisson processes MT of A1 and MT of A2 are going to be independent. So it means that you can think of a Poisson point process as a cloud of independently scattered points in your space. So independent scatter means that if I look at how many points lie here and there, and these two sets are disjoint, then I'm going to have independent random variables counting the these two. And the first property says these are not just independent random variables, they're Poisson variables. Okay, so this is the most common examples of point process. And so what you can see from property one is that if I have a Poisson point process, then for every A, the intensity of MTA is given by some number mu of A. The second property means that if I take A and B, which are disjoint, then mu of A plus B is sum of mu of A and mu of B because they have independent Poisson processes. And the sum of two independent Poisson processes will have an intensity that is the sum of the intensities. So this implies that this map, so the intensity associated to the counting process on a set A, this is in fact a measure. And so what we ask for is that if A is compact, then this is finite, but it can be infinite on non-compact sets. So it defines a Radon measure. So a Radon measure is a measure which is finite on compact sets. And we call this measure mu the intensity, the measure of M. Okay, so mu of A gives you the intensity of the counting process MT of A, and for each A. Okay, so it tells you how the points are scattered across your space. It is not a probability measure. I did not say it's a probability measure, and we don't even assume it's a finite measure. It can be infinite. We allow the Poisson processes to be infinite intensity. It's just a measure. Okay. So any questions about this? I guess some of you have seen the Poisson point processes before, but if you're not, you have a question about this. I don't see the chat, but okay. So why are we talking about this? Why do I need this notion? Because, well, Ito's main result was the following. It's really a stunning result, one of the most beautiful results I know of in stochastic analysis. It's really stunning, and I'll explain why it's stunning. What he showed is that if you take now a standard Markov process, and okay, we're going to make some assumption. We're going to assume that it's recurrent at 0, meaning that if you start from any point delta, any point which is different from 0, you reach 0 in a finite time. This is not essential, but if you don't have this property, then it's pretty boring, because if you, for example, if you visit 0 only once, then you don't need to define this point process of excursion because you only have one excursion. So in order for the theory to be interesting, you hope that you will visit 0 infinitely many times. So if you restart the process from any point away from 0, it will always come back to 0 in a finite time. Then you and then you assume that if you start from 0, it will reach at least 1 point delta in a finite time. So this way you have some interesting behavior. It doesn't get stuck at 0. It doesn't get stuck at any other point. It just continues to go back from 0 to delta, delta to 0. And this is exactly the situation which we're interested in. So this assumption of recurrence makes the process interesting. So under this assumption, the Markov process will visit 0 infinitely many times, and so you will have an infinite collection of excursions. So you can define this point process of excursions that we define here. This, okay, and Ito's main result was that, well, you know what? If S is a Markov process with stationary transitions, actually that's not even that necessary for this. If S is a Markov process satisfying this assumption, then the excursion process of S is a Poisson point process. Now, more precisely, it's a Poisson point process, not in time, normal time, but in this indexed by this occupation density. So E lambda is indexed by the occupation density lambda. So it's a Poisson point process in occupation time, but it's a Poisson point process nevertheless. What does that mean? Well, I defined in the previous slide what you mean by Poisson point process. It means that there exists some measure nu on the space of excursions. So first of all, it's a Poisson point process with values in the space of excursions. So it means that on the space of excursions, there is a measure which will be the intensity of this Poisson point process, such that, if you take any set, any subset by gamma, this is a set of excursions, then if you count the number of excursions which fall in gamma up to time L, here time is really occupation time, this counting process will be a Poisson process with intensity nu of gamma. And nu of gamma can be infinite or finite. If it's finite, then it's a classical Poisson process with intensity nu of gamma. If it's infinite, then, well, we still call it a Poisson process, but it can be infinite. And we call this, so this intensity measure of the Poisson point process is called the Ito excursion measure. So the intensity of a Poisson point process completely characterizes the law of the Poisson point process. So it means that there is a measure on the space of excursions, the Ito excursion measure, which completely characterizes the law of the excursions of S. Now, this is a very interesting result. So first of all, it's a very surprising result because S, it can be a continuous process. So S is like, think of Brownian motion, for example. So this result, of course, applies to Brownian motion. So think of Brownian motion or some continuous process like Orshad-Ullmann process. Okay, you have a continuous diffusion. And then out of the stomach of this continuous diffusion is coming out a purely discontinuous object. It's a point process, which completely describes this continuous process. So it's really a stunning result. It's a very surprising result. And if you apply this to Brownian motion, for example, you take S equals Brownian motion. Of course, this result applies because Brownian motion is recurrent. It will come back to zero from any point in finite time. Then you obtain that the excursions of Brownian motion are described by some infinite dimensional Poisson point process. It's a really surprising result. So this result, what does it really mean? Well, it means that we know everything about the excursions of this Markov process as soon as we know the Ito excursion, the measure nu associated with S. For example, well, one of the things we know about the Poisson process is that the intervals between the events are exponentially distributed with parameter nu of gamma. So it means that if I look, for example, here's one example. If I say, what is the occupation time lambda I have to wait until I see an excursion of type gamma? So when is the first excursion which will fall in this set gamma? How much I need to wait? Well, it says, well, because it's a Poisson process, this corresponds to a first event of a Poisson process. It's an exponential time with the parameter nu of gamma. So it means that if you give me a set of excursions gamma, and I say, how much do I need to wait until I see an excursion of S in this set? Well, you need to wait an exponential time, which has this law. Okay, so also, it says that if I take two sets of excursions which are disjoint, for example, excursions which stay below 1 and excursions which reach 1, these are disjoint sets of excursions, then the counting processes associated with these two are independent. The number of excursions below 1 and the number of excursions above 1 are independent random variables. So this is a very important fact. And more precisely, we actually know that if you fix a property of an excursion, so set gamma, and you say, okay, for example, the excursions whose duration is longer than 1, this is a type of excursion. Well, the number of excursions satisfying this is a Poisson-like random variable. And in fact, if I look at up to an occupation time L, and I look at the number of excursions which have this property, they will form a Poisson process in the variable L. So it gives us a lot of information, and we know everything about the Poisson process. We can compute everything we want. It's very explicit. So it means that we can actually do computations with excursions given this result. So it's a very, very interesting result because it opens the way to calculate lots of properties of excursions once you can describe the Ito excursion measure of S. So the big question is, can we describe the Ito excursion measure? What do we know about the Ito excursion measure of S? Well, that's the focus of excursion theory. So really, so this is a picture. I have a friend, Irene Klein, who's a mathematician in Vienna. She is also an artist, so she draws these very nice math. So she writes. Actually, she makes math cartoons, always related to stochastic analysis. So very specialized cartoons. And so this is a picture she drew after following lectures of Markov on excursions. And so this is a really good illustration of excursion theory. So the way Ito thought about excursions is this: instead of thinking of a Markov process through an infinitesimal description or transition probabilities or generator or SDE, he thought, well, another way of describing the Markov process is I fix a base point in 0, for example, and then I think of the Markov process as a succession of independent excursions from this base point. Every time I hit 0, I start a new, so the Markov probability says that I start a new excursion independently from the past. So I have this Markov process coming always back to this base point, and then branching out. So you see each of these staircases is one new excursion, and the base point is Ito's hand.
Rama, there is a question in the chat.
Yes.
Okay.
What's the justification that the waiting time follows an exponential distribution?
So it's not the justification; it's the property. So it's a consequence of the Poisson property. So this is related to the fact that the excursions are independent because of the Markov property, and the duration of the excursions are not exponential. This is in occupation time. So they are exponential in this time change, which is the occupation time. We will see that in real time, they're not exponential, they have another distribution, and the change between real time and occupation time is the occupation density, LT. So LT is not deterministic, so when you change times, you will get a non-exponential distribution of the durations in actual time. I don't know if that was clear. So the distribution of the durations of the excursions in real time is not exponential. All these parameterizations is in lambda, the occupation time. Okay. So this is not an assumption. This is a result. So Ito's result is that you take any Markov process, you look at the excursion process defined in occupation time, not in real time. In occupation time parameterization, it's a Poisson point process. And then we will go back to real time and see what it looks like. But when we go back to real time, we will lose the exponential property, but we will not lose the independence. I'll come back to it in a couple of slides. Does that answer the question?
Yes.
So so this, you get it for free, the exponential, because basically the proof of the result. So I'm not going to give the proof here, or maybe tomorrow if I have time. The proof of the result is the following. You look at the counting process of excursions, this process. Okay, you look at this process which counts the excursions in occupation time. So this is a counting process, and then you have this this characterization. So if you look at accounting process, the question is, when is this a Poisson process? Okay, so there are many ways to show that some counting process is a Poisson process, but one characterization, which is the one Ito used, is to say that if a counting process has stationary independent increments, then it's a Poisson process. So the Poisson process is the only counting process, only integer valued process, increasing integer value process, which has independent stationary increments. So you look at this construction and then use the strong Markov property to show that, and the stationarity of the transition probabilities of S, to show that this, if S is a strong Markov process with stationary transition probabilities, then this process has stationary independent increments. And being a counting process with stationary independent increments, it means that it is some Poisson process. That's the only thing. But then once you show that it's a Poisson process, then you get for free that the inter-event times are exponential. So that's how it's really very surprising first time you see it. But so that's how we get it. So this is a consequence of the fact that there's only one counting process with stationary independent increments. That's possible. Okay, so that's this is really the vision here, is that you think of the Markov process as an infinite collection of excursions, always coming back to the base point, which in this case is 0. Okay, now this result seems very exciting because we think we know at least what the Poisson process is. So if we can get the intensity of the Poisson process, then we can calculate anything. So the question is, what do we know about this famous intensity, what's called the Ito excursion measure of S? Can we characterize it? Can we derive properties of it? If yes, then I can go back to all the quantities I'm interested in, and I just calculate. It brings it to elementary calculations involving Poisson processes, which is very easy. So instead of manipulating SDs and PDEs and complicated infinitesimal descriptions, I do elementary calculations with the Poisson process. So it seems a good idea. But we need to describe first this Ito excursion measure nu, because the intensity is always nu of gamma, so I need to describe what this nu is. So our problem is this is an infinite dimensional measure. And in fact, as you see, I do not say that it's a finite measure. In principle, it can be infinite. So there are some issues here. And maybe after the break, I will go into some of these issues and say what we know about this nu in general, in some examples, and what how we can deal with it. But the study of this Ito excursion measure has been the focus of huge literature since the 70s, especially in the 80s and 90s. There was a lot of progress concerning Brownian motion mostly, but also concerning some diffusion type processes. So I will very briefly describe some of these interesting results, and then we will use them to apply them to specific models which we're interested in finding. Okay, so let's take a break now. That's a good idea. And then we come back. In 10.
Okay.
Yeah.
10 minutes break. Okay.
Thank you. So this key result by Ito, which is the foundation of the theory, and so it's an existence result, but it doesn't describe what this analytical object is, but it gives us a lot of hope to be able to describe in very detail the structure of the excursions if we can get hold of the Ito excursion measure. Okay. Now, before getting hold of the Ito excursion measure, the fact that we know that there is a Poisson point process description of the excursions is very powerful, because it allows us to derive a lot of properties, because a Poisson point process is well, it has independence of increments, stationary increments, and it has a very specific form of the law. So it gives us a lot of interesting properties without making specific assumptions on S, other than the fact that it's a Markov process. So in particular, it gives us a description of the delta excursions. So remember, we are interested not in all excursions going from 0 to 0, infinitesimal ones, but the excursion would go 0 to delta and come back to 0. So they have some finite distance away from 0. But as we saw yesterday, these delta excursions are linked via the last exit decomposition to the set gamma delta of excursions from 0 to 0, which reach the level delta. So if we define the set gamma delta, this is a subset of the space of excursions. So we're interested in counting the number of excursions from 0 to 0, which fall in the set gamma delta. And yesterday we showed that if we can count these, we can count the delta excursions, because each delta excursion contains exactly one of these. Now we have a tool, because we know that if we count the number of excursions which fall in some set, they form a Poisson process in the occupation time variable. So now this will tell us a lot about the process of delta excursions. So the result is the following. It says that, so if you take, again, so the assumptions are the same here. You have a standard one-dimensional Markov process with, which is recurrent between 0 and delta. In this sense, if you started from 0, it reaches delta in a finite time. If you started from delta, it would reach 0 in a finite time. So that's the only assumption, no more information needed. So then you can say the following things. So if you call nu the Ito excursion measure associated with this Markov process, then remember nu of a set is the intensity of the Poisson process associated with this set. So good news is that nu of gamma delta, this set is finite. You cannot have an infinite number of excursions which reach delta in a finite time, because the process is continuous. It cannot do. So this nu will be finite. So then if you look at the number of excursions which reach the level delta up to occupation time L, this is a classical Poisson process. It's not an infinite one. It's a finite, well-behaved Poisson process with intensity nu of gamma delta. That's what Ito's theorem says. And now we're going to relate it with the number of delta excursions. Well, what we saw is that the number of delta excursions is exactly equal to the number of excursions falling in this set gamma delta, because each delta excursion contains exactly one element of gamma delta. So the number is the same. The difficulty is that this process here is in occupation time, whereas what we're interested in is the number of delta excursions in normal time t. Well, to convert normal time t into occupation time, well, we can do it through the occupation time. So counting the number of delta excursions up to time t corresponds to counting the number of these excursions in gamma delta up to occupation time LT of S. Or if you fix the occupation time level L, counting the number of excursions in gamma delta up to occupation time L corresponds to counting the number of delta excursions up to time tau L. Well, tau is the inverse local time. Okay, so we can go back and forth between time and occupation time using LT in one direction and tau in the other direction. Okay, so up to this time change, you know exactly what's going on. So it means that the number of delta excursions for any Markov process is a time-changed Poisson process. And the time change is, we know what it is. It is exactly the occupation time at 0, or local time at 0 if you want, of S, of the signal. So we have a complete description here of this process. So now what does that tell us? Well, that tells us a lot about this process, number of delta excursions, which I recall in the strategies we looked at. This corresponds to the number of transactions up to t. Well, it tells us that, well, first of all, if you look at this process, d delta, in under the time change, which corresponds to the inverse local time. So the number of delta excursions up to inverse local time tau L, this is just equal to NL. So NL is a Poisson process. So this is just a Poisson process with intensity nu of gamma delta, the excursion measure computed on the set gamma delta, this set. So this is a Poisson process, but this is not what we're interested in, because we're typically interested in counting the number of trades up to a given time, not up to a given inverse local time. Well, no problem. You can switch back to regular time by doing a time change. When you do the time change, because the time change is an increasing process, you don't lose independence. So the intervals in between these events, so it means the duration of the excursion, delta excursions, the events that are counted by the delta, are still going to be independent, but they're not going to be identically distributed anymore necessarily if you have time dependence in the tau L. And they are not going to be exponentially distributed anymore. So the Poisson process has exponentially distributed inter-arrival times. But if you do a time change, then you lose this exponential, because the time change here is random. It's the local time. It's the inverse local time. And also, we don't know anything. The inverse local time can be super complicated. It's just increasing. That's all we know. So you lose the exponential distribution, but you still have the independence. So what you get is a counting process whose intervals are independent, but not necessarily exponential. So this is what's called the renewal process. Okay, so slightly more complicated, but still very tractable. You know a lot about the properties of renewal processes. They are based on sums of ID variables. So still not bad. So it means that in general, in the general case of any Markov process, S, the number of delta excursions is going to be a tractable object. It's a renewal process. Under P0 means that we start the process from 0. We start the signal from 0. If we don't start it from 0, well, you need to throw away the first part, because until it reaches 0 for the first time, it can have a different law. So that's why I state the things under P0. But it's always going to have independent inter-arrival times. But if I don't start from 0, if I start from another point, then the first hitting time will be different from the others. So that's why I say under P0. And so what this means, what property 2 means, is that more explicitly, the durations of the delta excursions are independent and identically distributed variables. And in fact, we can calculate their moment generating function. So remember the duration of the excursion is the difference theta I minus theta I minus 1. So the first one is theta 1 plus. So you can, in fact, calculate the moment generating function in terms of the Ito excursion measure nu, and you have this formula here involving the first hitting time of 0. I'm not going to go into the proof of this. It's not necessarily very interesting, but it says that delta excursions can be completely described in terms of the Ito excursion measure nu. The only thing that appears here is nu. Okay, so this tells us what happens. So the difficulty a little bit with the Ito description is that it's not in time, it's in occupation time, but the time change you need to go to switch between occupation time and real time is this tau L. So if you understand how this time change works, then these results are easy. Okay, so conclusion is that, well, even under real time, not occupation time, it's still tractable. We have that the distributions of these delta excursion, the duration of the delta excursions are still IID. They have some moment generating function, which is explicit in terms, explicitly expressed at least in terms of the Ito excursion measure. So again, if you give me a description of the Ito excursion measure, then in principle, I can calculate all this. So this is good because it means that if we can get hold of d delta, then we can start computing a lot of things. At least we can calculate the realized profit. We can do a lot of things. Now, what does, so what we showed in the first lecture is that any continuous path can be decomposed into concatenation of delta excursions. There's a decomposition of any path into delta excursions. And of course, I can still apply to the path of my Markov process. But now, this decomposition becomes even nicer because now, if S is a Markov process, which is, but to which I can apply the Ito result, then this decomposition becomes an IID decomposition. So now the same result says that now if I now apply this to a Markov process, strong Markov process, with some nice properties which say that it comes back to 0 infinitely often, then in fact, the decomposition we saw in lecture 1 is a decomposition of the path into IID concatenation, a sum in the sense of concatenation. So these are paths. Each term is a path in this sum. I'm taking the path of my Markov process. I slice it at the delta x. I slice it into delta excursions. This is what we did in lecture 1. But now each slice is now a random variable in the space of excursions. And the previous statement is that these random variables are in fact IID variables. And so it means that now I can slice any Markov process into an IID sequence of delta excursions. And I can express the Markov process as an infinite concatenation of these IID sequence. And I concatenate them at the hitting times, at these level crossing times that we defined yesterday. And these are the times, the start times of the delta excursions. Now, what is the difference between this and the Ito result? Well, the difference is, the big difference is that because now I'm looking at delta excursions, and because I can only have a finite number of delta excursions per unit time, well, first of all, what we saw is that the number of delta excursions is a renewal process, so it's a finite value renewal process. It's not going to blow up, no infinity here, because I don't care about the infinitesimal excursions which just jump around zero. I only care about those which delta, and those will be finite almost surely. So now I have a sequence. It's not a continuum of family of excursions, but it's a sequence labeled by integers. I can label them in order. So very easy to deal with. It's the IID sequence, IID sums, the simplest thing you want to have. And so now, since I have IID sum, now it's completely described by a distribution, the distribution of each term. Because all the terms have the same distribution. There is an object, pi delta, which is the distribution of the delta excursions of my process S. All the delta excursion will have the same distribution. This is a distribution this is a probability measure which is concentrated on the space U delta of delta excursions, which we defined before. And once I have this distribution, then I have everything I need to recompose the path of S, because I draw random variables according to this distribution pi delta, and I sum them and concatenate them according to this concatenation rule. And I concatenate them when? Well, at these points, which are defined by the lifetimes of these random variables. Each random variable is an excursion. The lifetime is lambda EI for the ith excursion. And all the information I need is in the random variables. I draw these random excursions. They have a lifetime. I concatenate at the end of the lifetime the next one, and so on. So it means that I have another way of constructing the process S, not through transition probabilities, not through generators, not through SDs, is I give you the distribution pi delta of the delta excursions. You find a way to generate samples from pi delta, and then you paste them together. You stick them together, you concatenate them. And this is very interesting because it's a global construction. It's not an infinitesimal or local construction. And we will use this but tomorrow and the last lecture to construct new models. So instead of giving you an SD, I say, give me a distribution on the space of delta excursions, and that's all I need. And then I generate IID sequences from pi delta and paste them together. We will see that this is a valid way of constructing Markov processes, and we will see how it works. Now, but here I'm doing the opposite. I start from a Markov process S, and then I want to break it. I decompose it into an IID concatenation. And what is the distribution of each term in this sum? Well, each term in this sum is just one delta excursion. So the law of each term in this sum is exactly the law of the first delta, the first or the second, whatever, they all have the same law, the law of the first delta excursion of S. So what is the law of the first delta excursion of S? Well, you start S from 0, so it's P0, according to the notation, the Markov notation. So you start S from 0, and then you let S go until it reaches the stopping time θ1 plus. What's θ1 plus? It's the one we defined yesterday and the day before. It's the first time it reaches 0 after having reached delta. So so we stop it at this time. So the law of this stop process under P0 is what we call the law of the first delta excursion. So this is pi delta. This is pi delta. And so now if I have any quantity which can be expressed, any quantity which is any function of excursions, for example, h can be the maximum height of an excursion, the duration of excursion, any property of excursions h. Well, its expectation with respect to the law pi delta is nothing else but the expectation under P0 of h computed along the stopped process, stopped at p2 1 plus. So this is exactly the description of pi delta. Okay, so in summary, this decomposition, the pathwise decomposition we saw in lecture 1, which is quite explicit in terms of delta excursions, in the Markov case, it translates into an IID sum in the sense of concatenation now, and the terms are ID, the distribution of each term is exactly the law of the first delta excursion of the Markov process, means the law of the process starting from 0 and stopped at the first time it hits 0 after having reached delta. This gives you a complete description. But this description, I hope you understand that this is a very interesting description, because on the left, I have a Markov process, which can be pretty complicated. On the right, I have an IID sum. And IID sums are, but we love that in probability because that's the easiest thing to do. IID sums are, you give me the distribution, I can calculate everything here. So this is so this means slicing the path along this times theta k plus is the right thing, because then I get IID components and I can play with them easily. Now I need to describe the distribution pi delta, and then I'm done. Okay. So, so what we see here is that this description can be interesting for the decomposition purpose, but it's also interesting for the modeling purpose, because I can do the opposite. I can do a synthesis. I can choose a model for pi delta and then construct S like this. And, I already have the description I need because I model pi delta. I don't need to sweat in order to, calculate pi delta from, say, the generator of S. I already have it. So we will use this by tomorrow and on Friday. So, but if you look at the theoretical literature on excursions, they went the opposite direction. They start from a Markov process. Typically, it's Brownian motion or some diffusion model. And then they try to describe these objects, the Ito excursion measure, distribution of excursions in the infinite dimensional space of excursions. So, okay, so I'm going to say a few words about these results before going to the opposite point of view, but I'm a proponent of the opposite point of view, which is not classical, it's just building processes from excursion. But nevertheless, I'm going to say a few words about this classical theory, which is very rich. So how can we describe this Ito measure, which describes the intensity of the point process of excursions? So there are many descriptions. Typically, these descriptions take one property of the excursion, either the duration or the height, maximum height, and then they condition on that. So first they derive the distribution of that quantity. What is the distribution of the maximum height of an excursion of S? What is the distribution of the duration of an excursion of S? So first you try to work out that, then you condition on that, and then you obtain a probability measure, which is the distribution of the excursions with a given height or with a given duration. So that's an approach that has proved useful, especially if the process has some self-similarity property. Then the conditioning, you can get some nice property out of it. Okay, so the first approach, which is to condition on the distribution of the duration, was the one used by Paul Levy historically. So Paul Levy studied excursions of Brownian motion. So his idea was to say, well, Brownian motion is self-similar. So I just need to study this excursions of duration 1 over 0, 1. And then I can deduce all the properties of other excursions by self-similarity. So he introduced the normalized Brownian excursion, which is an excursion which goes from 0 to 1. And that is a Brownian bridge. So then in that case, you know a lot about it. So more useful representation for our purpose is a description given by David Williams in the 90s. So he did the opposite. He said, well, I'm going to be interested in the maximum height of an excursion. So if I call the maximum of an excursion capital M, this is a random variable. So Fm, let Fm be the distribution of the maximum excursion height M. So he said, well, I'm going to first work out the distribution of the maximum excursion height. And in the case of Brownian motion, this is explicit, or you can work out in some case of other diffusions. And then you condition on M. So it means you normalize vertically instead of horizontally. And then you have you look at the set of excursions with a maximum height M fixed. And then you look at the distribution of the excursions conditional on this height. And this is what I note here, QM. QM is then a probability measure, which is concentrated on the set of excursions which reach M. And for us, as you can guess, this is a better description because we're interested in delta excursions. So we're interested in excursions which reach the level delta. If they don't reach delta, we're not interested in them. So this means we are really interested in slices. So this is what I call slicing. You can slice according to the duration, or you can slice according to the height, or you can slice according to other variables. And the slicing according to the height is what we are interested in for our purpose, because we're interested in the sliced delta more precisely. And in fact, what we're going to see is that, in fact, you may not need to know QM very precisely. For most of the calculations involving loss, risk, drawdown, so on, really they only depend on M. They only depend on the maximum height. For example, if I want to tell you what's the worst loss in an interval, I don't really care where in that interval I reach that loss. I care about what's the worst loss. So then I don't need to know QM, I need to know FM. So this simplifies a lot because FM is known for many examples. QM can be very difficult to but pinpoint. QM is known for Brownian motion and for some very specific processes, but in general, QM is a very complicated object because it will be the law of a process conditional on it reaching a certain maximum. In general, if you're familiar with these things, you can imagine it's a nightmare. Okay, so I will nevertheless show some results for interesting classes of processes, and they constitute the examples used a lot in finance. So sorry, how am I doing with time? Let me check the hour. Okay, so I will go a little bit. Okay, so now I'm going to show some results for diffusion models. And if you look in the literature, analytical literature on excursions, well, as I said, most of the literature, so Ito's theory was constructed in the case of general Markov process. So the work of Ito himself is really for general Markov process. But subsequent work after Ito was like 90% of the work is on Brownian motion. Really. They studied excursions of Brownian motion. It's already a very rich topic because describing Ito's excursion measure for Brownian motion is not trivial at all. It's the subject of many monographs and so on. So it's mostly Brownian motion. Then there are some results for linear diffusions, meaning Ornstein-Uhlenbeck, basically. And then there are other results for Levy processes. I will not talk about them here because this will need an entire, set of lectures. So the excursions of Levy processes are also studied in detail. There are a lot of identities there, which are interesting. But that's all. I mean, for general, since Ito, there's not been much progress on the general Markov process case because it's analytically very challenging. Okay, so these 8 examples I give you are practically the only examples for which we can actually describe things in detail, aside from the Levy case, which I will not describe here. Okay, so now what do we know for one-dimensional diffusions? Well, for one-dimensional diffusions, the analytical theory is very well developed. So we can say a lot of things. And this is good because most of the applications in finance use such models. So it's a very useful framework. So, so now I'm going to look at the case where S is a one-dimensional diffusion process, which is described by its infinitesimal generator. So there is a drift coefficient B, and there is a volatility coefficient, which would be square root of A. So A, you can think of the square root of volatility, the square root of the vol. Oh, sorry. A is square of the vol. Okay. So I assume that A is strictly positive, B is L1. And so the classical way to study this, which was pioneered by Feller, is to transform this. You can think of it as transforming it into a Brownian motion by change of variable. This is only possible in dimension 1. And so the idea is that you do a change of variable, you write G in the canonical form. You can write G as in this form. So this you can do the calculation by yourself if you've never seen this. This is the classical form used by Feller. So you define two functions. One is called the speed measure M, which is 2 over S prime A, where S prime is this, and then the scale function, which is S, whose derivative is this. Okay, so scale function is defined up to a constant. The derivative is given here. So usually you define it to have a value 0 and 0, but that's not necessary. So the idea is that the M, so you can think of any one-dimensional diffusion as a time-changed Brownian motion. Okay, this is always true. And you can think of the time change as this function M. And you can think of the vertical scaling as this function. So if you scale time and space through M and S, then the idea is that you get back a Brownian motion. So then you map all the properties you know from Brownian motion to this through this change of variable. So so the first thing is that you want to get hold of these hitting times distributions. So here's that. What we want to say is, in this case, if you have a one-dimensional diffusion, can you describe the distributional properties of excursions and delta excursions? So their delta excursions are defined in terms of hitting times of the level delta. So you need to know the distribution of the hitting times. So the hitting time distributions are known analytically in terms of their Laplace transform. So if you, again, remember we defined TYS is the hitting time of the level Y starting from 0. And all of these hitting times are described in terms of what's called, so these are called the Wiener-Hopf factors, so phi lambda plus phi lambda minus are a pair of functions which are solutions of the eigenvalue problem for this operator G. Okay, so you solve the eigenvalue problem for G, you get two solutions for each lambda, and which have the different symmetries. And this this gives you the Laplace transforms of the hitting times for any level in terms of ratios of these Wiener-Hopf factors. Okay. So what is X and Y here? Well, if you start the process from X and then you look at the Laplace transform of the hitting time of Y, then this is given by the Wiener-Hopf factors computed at X and Y. Okay, so So if x bigger than y, with x smaller than y, you have the inverse. So this is a very useful thing. So it means that as soon as I can solve this eigenvalue problem here, then I can compute phi, then I can get hold of the Laplace transforms, which then through an inverse Laplace transform gives me the distribution of the heating times. So this is for any heating time starting from any point. So now I'm going to apply this to the variables I'm interested in. So remember, in our problem, we start each trading cycle, you start from 0, you do but nothing until you reach delta, and then so that's called the waiting period.
So, sorry, there is a question related with this. Is what does we use Laplace instead of characteristic function here?
Well, you can use the characteristic function. I mean, these are positive variables, so the heating times are positive variables. So it's more natural to use the one-sided Laplace transform because these are times. But yeah, of course, the characteristic function is the same with I here. Then you will get you will get a complex version of this. Yeah, but here because you have times, heating times, it's more natural to use the Laplace transform. And in fact, all of these times are, all these distributions have an exponential tail, so the Laplace transforms are finite. So, okay, so in our case, we're interested in two particular levels, 0 and delta. We start from 0, and the first time we reach delta is the holding period. So that's what we call tau k minus theta k minus 1. Then from delta, you short the portfolio, and then you hold it until you reach 0 again. That's what we call the holding period. So that's theta k minus tau k. And the total length of a trading cycle is therefore theta k minus 1. So as you can see, these correspond to heating time. The holding period corresponds to the heating time of delta starting from 0. The waiting period corresponds to the heating time of 0 starting from delta. And the total cycle is the sum of the two, which are independent because of the Markov property. So it's just the Laplace transform is just the product of the first two. So you can now calculate these in terms of the Wiener-Hopf factor. So the holding period given by the Laplace transform, the holding period is given by simply the ratio between the Laplace, the Wiener-Hopf factors at 0 and delta. For the holding period, it's the Wiener-Hopf factor plus delta divided by A0, and then if you want the whole period, you take the product because of independence. So this is easy. As soon as I have the Wiener-Hopf factors phi, I can calculate these things easily, and I will show you that we know these phi factors for example, Ornstein-Uhlenbeck and some other examples. But these formulas are general for any diffusion. This works. So as soon as you get hold of this numerically or analytically, you can calculate these Laplace transforms. Then we're interested to remember in the number of delta excursions, because this is the number of transactions. Now, the number of transactions here, so the number of trades, in this case, what we saw is that for any Markov process, in particular for these one-dimensional diffusions, d delta is a renewal process. So it's a process defined by discrete events, and the intervals between the events are IID. So if we call the intervals distribution of intervals f theta, so remember f theta is a variable which has a Laplace transform, which we wrote in the previous line. This is the Laplace transform. So this f theta, well, there's a well-known relation for renewal for a renewal process, which gives you an equation solved by the expected number of events, and that's called the renewal equation. So the renewal equation is an integral equation, which you can then differentiate, gives you a differential equation for the for the expected number of events. So in this case, the expected number of transactions. It says that the expected number of transactions at the time t is f theta t plus integral from 0 to t of n delta. This is a convolution integral. The convolution of n delta and f theta. Okay, and this equation simply is an analytical translation of the fact that the intervals are IID. Okay, so it says that the number of the d delta is the sum of ID intervals. So if I want to look at the next one, it's the current sum plus an independent term, and when you translate it into distributions, you get this convolution equation. And in particular, this equation leads to an explicit equation for the Laplace transform of n delta, because if you move n delta to this side and then you take the Laplace transform will transform the convolution into a product. So you get that, well, the Laplace transform of n delta is the Laplace transform of f theta divided by 1 minus the Laplace transform. So you get this simple equation, which tells that if I know L theta, which is on the line above, I also know the Laplace transform of the number of traits, because it is just a simple algebraic transformation. So it means that as soon as I know these 5 functions, I know a lot of things: distribution of the waiting times, trait times, holding times, and expected number of traits, and so on. So everything is analytical. Now, starting from these 8 expressions, I can calculate a lot of interesting things. For example, well, all the things we listed in lecture 1. For example, if I want to look at the maximum loss per trait cycle, so a trait cycle is 1 delta excursion, goes to delta and comes back to 0. What is the maximum loss during this trait cycle? Well, first of all, we know that because of the Markov property, the maximum loss for all traits cycles will be IID variable. So I just need to look at one typical trait cycle, and from the properties of the process, we can derive an explicit expression in the diffusion case of this maximum loss. So the probability that the maximum loss during each trait cycle exceeds X is simply a ratio of the scale function S at levels delta and X plus delta. So this is a simple expression. If you give me the scale function S, I can compute these maximum loss probabilities in a very simple way. Another example, which is very useful, is the distribution of the realized profit. So what is the distribution of the realized profit? Well, you want, so let's call pi mk the distribution of the realized profit of the strategy with a stop loss level m. So if you don't have a stop loss, then it's very simple, because the realized profit at each cycle is exactly delta. So the distribution is simple because it's deterministic. So this question of distribution of a realized profit becomes interesting if you introduce a stop loss, because if you introduce a stop loss, then, well, 2 things can happen. During a trade cycle, if you do not reach the stop loss level, so if your signal doesn't go to the level delta plus m, then you just hold it until it comes back to 0, you make delta, and then you unwind the position. If you do reach the stop loss during your excursion, then you cut the position, then you have to close your position, you unwind the portfolio, but then you've lost M. Then you've lost M. So it means that there are two things that can happen. Either you do not reach the excursion does not reach M, and then you make delta, or you do reach M and then you close the position, you lose M. So it means that over each trade cycle, your loss is a Bernoulli variable, which is either delta, positive delta, or minus M. And because of the Markov property, these variables are independent. So your distribution of realized profit is super simple. It's just a collection of ID Bernoulli variables. The only thing you need to calculate is what is the probability to hit delta, what is the probability to hit minus M. And the result above tells you what this probability is, because it's just this expression computed for x equals M, because it's the probability that the delta excursion reaches M after having reached delta. And this is the ratio of the scale function at these 2 points. So you can see that as soon as I give you the scale function S, you can calculate all these things. And this is very interesting because these are very useful quantities. In general, if I give you, if I tell you to compute this starting from an infinitesimal description, it's not easy, but if you know the scale function and if you know this trick, then it's trivial. In particular, this leads to a binomial profit-loss distribution after n trade cycles, which is just the sum of these ID variables. So very easy. But the number of terms in this binomial sum is random. It's the number of trades. But for example, the expectation is, you can compute it explicitly because it involves the expected number of trades times a certain expression involving, again, the scale function. So this is interesting because this is a very interesting quantity. How much do I, what is the distribution of loss after n trade cycles? Well, I can, I have a simple expression here. Now, note that if I ask you the same question for a fixed time, it's more complicated because then I have to count the number of times and so on. So if I take n, then the first term is n. So if I condition on n trade cycles, then the first term is n. If I ask you at a fixed time t, then I have to compute first the expected number of trades, and then this is done by solving the Laplace transform on the previous page, this. And then I have to multiply by this. But still, it's doable because we know the Laplace transform of n delta, and this is very explicit. So as soon as I know S, the scale function and the speed measure, then all these things are accessible at least computationally by inverting a couple of Laplace transforms. And in some cases, as I will show explicitly in the case of Brownian motion and OU. So how am I doing with time? Okay, so maybe I'm not gonna go into the OU example because that takes a long time. I'm just gonna show you one example. Yeah. So the most well-studied example in excursion theory is probably Brownian motion. There are entire books about the excursions of Brownian motion, the E2 excursion measure, or everything you can imagine has been studied. Especially there are lots of interesting work by Markov and Jim Pittman on this. In the references, I give a very nice survey article of Pittman and Yo on Brownian excursions. So for us, it's not a very interesting example because if your signal is Brownian motion, then it means that there's no mean reversion. I mean, the whole point of these training strategies is you detect a signal which mean reverts to 0 or some level, and then you trade on that. If your signal is Brownian motion, it can go away from 0 for a very long time without coming back. So it's really the worst case. But it's a very important case because, see, what happens in these training strategies is that people take a signal which they assume to be mean reverting. They use the Ornstein-Uhlenbeck or some mean reverting process as a model, and then they calculate this, simulate everything under the model. But this model assumes there is mean reversion. So what's the worst case scenario for such a strategy? Well, the worst case scenario is when mean reversion is not there, because you bet on mean reversion and it's not there. So in fact, the Brownian case is a very instructive case. So I'm going to comment on it for a few minutes because it corresponds to the model risk of these strategies. Is that you assume there is mean reversion, you bet on it, and actually it doesn't happen. So the drift is 0, unfortunately. You thought it's negative. Okay, so what happens when there's no mean reversion? Well, this means you think S is going to mean revert, but the drift is 0, unfortunately for you, but there is a volatility. So the answer is bad things happen. What was going to happen? First of all, one of the things, the first thing you can derive in the case of Brownian motion is that the durations between the length of a delta excursion, well, as we know, they're IID, but in the Brownian case, you can derive explicitly the distribution. It's a 1/2 stable distribution. So if you're familiar with stable distributions, you know that it's a family of distributions which have an index ranging from 0 to 2, but they all have the nasty property of having infinite variance. And if the index is smaller than 1, they have infinite mean. So it means that the durations of delta excursions for Brownian motion, for any delta, any delta strictly bigger than 0, you need to wait a time which is so heavy-tailed that it has infinite mean. So that's not good because it means that you think it's going to mean revert, but you're going to have to wait a very long time, and the time may have infinite mean. So on average, you may have to wait an infinite time. It doesn't look good to start with, but it gets even worse. How about the height of the delta excursions? Well, the height of the delta excursion translates into the maximum loss of your strategy, because if you think it's going to go back to 0 and it goes the opposite direction, well, you're going to lose money until it comes back. So the maximum loss is the maximum height of the excursion. And this result says that if your signal is really Brownian motion, then the maximum loss you can have, or the maximum height of the excursion, has a Pareto distribution. So it's a power distribution with tail index 1. So more precisely, the tail of the distribution is delta divided by m plus delta. So the probability of having a height bigger than m is delta divided by m plus delta. So it decreases very slowly as m goes to infinity as 1 over n. So this is very bad because it means that, again, the expected maximum loss is infinite. Try to integrate this guy to infinity, you will have a problem. So this is very interesting because, why? Because this is a strategy involving an asset whose price is described by Brownian motion. It can be it seems a very low risk thing, right? You're in Black-Scholes, not even Black-Scholes. It's a Bachelier model. You have a price which is Brownian motion. What can go wrong? I mean, Brownian motion has a Gaussian tail. I'm holding this asset. I don't hold anything else. How can I have a heavy tail distribution for the loss? Well, that's a very interesting example because it says that, fixed time distributions are the wrong thing when you think about dynamic strategies. Here we have a strategy which only trades one asset. The asset has a Gaussian distribution of returns. So you might wrongly conclude that the strategy will have a Gaussian distribution of loss. That is wrong because this is only true for static portfolios. Because you have a dynamic portfolio here involving hitting times and so on, it turns out that your maximum loss has a heavy tail distribution with infinite mean. This is very strange, huh? Well, this is very important, I think, as an example, because this example is exactly what shows that in these mean reversion strategies, model risk is much bigger than the risk of, than the tail risk under a given model. Because under any mean reverting model, this distribution is going to be exponential. We will see it tomorrow when we look at the OU model. So if you assume the thing is mean reverting with an exponential, with a linear drift, then the probability of going above a certain level m will decrease exponentially with m. But if the drift disappears because your assumption is wrong, then your loss will have a heavy tail with infinite mean. So this is really not intuitive. It's linked to the disappearance of mean reversion. It says that you can trade a single asset which has a Gaussian distribution of returns, yet the distribution of losses of your strategy is not Gaussian at all. It's heavy-tailed, and it has infinite mean. It cannot be worse. So this, I think, is a very important example. It shows that when you have dynamic trading strategy, even simple ones with one threshold, nothing fancy. So here we have a bounded position. So the position is either 0 or 1. So it cannot be simpler than that. Bounded position, one threshold, nothing very complicated. Even that leads to fixed time return distributions, which are very different from the actual distributions of your strategy. So the distribution of the underlying asset is not the correct benchmark for the risk of a dynamic trading strategy, because dynamic trading can completely change the distribution. Okay, and in fact, we already know this from options theory, because if you know options theory, delta hedging and Black-Scholes, well, if you're in Black-Scholes model, the Black-Scholes asset has a log normal distribution, but then the hedging strategy, which involves only cash and this asset, will have a distribution with bounded support, because you have a perfect hedge, so you have a zero probability of going below some level. So one of them has an unbounded support, the other one has a bounded support. So you can see that the distribution of a dynamic strategy can have nothing to do with the distribution of the underlying asset. And here's an example which is totally shocking, because you move from a Gaussian distribution through an infinite mean heavy tail distribution with just one threshold. So this means that really we should really care about the distribution of the excursion heights and not about the distribution of the increments of the process, because we do not sample the process at fixed times. We sample it at the hitting times. And so that's really what we should care about. So this example is important to keep in mind. And tomorrow I will continue with more common example, which is the Ornstein-Uhlenbeck process, which is used, as I said, in 90% of the papers on pairs trading. This is an example which is very explicit. We can compute everything in it, and we can analyze the properties of these pairs trading strategies in great detail, and especially the role of delta, the stop loss, the efficiency of the strategy, and so on. Okay, so I stop here for. Thank you.